So, this is our graph structure. Now, let us see in how many parameters can I represent each node. Remember that we have said that for every node we will represent probability of that random variable given all the parents. So, for earthquake, how many parameters do I need? Just one parameter. Why? Because earthquake has no parent. So, I simply want to represent probability of earthquake and probability of not earthquake, but they sum to 1. So, I basically need one parameter, same for burglary. So, we need 2 parameters for earthquake and burglary. Okay? Now, let us think about alarm. For probability of alarm, we have to say probability of alarm given all the parents. What are all the parents? Earthquake and burglary. So, how many parameters do I need? 2. People say 2. Okay. What are the 2 parameters? What's your name? Mayur, and the person in the blue shirt earlier, behind you? Chinmay. Yes, Chinmay. Why do you say we need 2 parameters? What are the 2 parameters? Earthquake and not earthquake, yes. Burglary, not burglary. So, how many such possibilities are there? 4. You said 2. Right. So, very important. So, what are the possible states for my parents? 0 0 0 1 1 0 1 1. And for all such possible states, there is a different probability of when the alarm is going to go off. So, we will end up having this kind of a condition probability table with the node alarm. It will be probability of alarm given earthquake comma burglary. If both earthquake happens and at the same time burglary happens, 0.95. If only earthquake happens but no burglary happens, 0.29, and so on and so forth. So, we need 4 parameters. How many parameters for John? Come on, this is not very hard. 2 parameters for John and 2 parameters for Mary. So, now notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters. We have 10 parameters to represent this Bayesian network. And what I am going to show you now is that that has the full power for representing the full joint distribution. That is the beauty of this. So, for that we have to ask some very basic independence questions. So, let us quickly say, is burglary and earthquake independent of each other? Right. By knowing earthquake, burglary does not change. Although people can say that in some ways it may be dependent also. Earthquake happened, burglar said, oh, this is a really good time, people have gone crazy right now, let me go and burglar the house. Possible, unlikely, but it is possible that there is some small effect, but we are not modeling that. We are saying they are independent events. Then by knowing alarm, does earthquake give me additional information on whether John is going to call? It is an important question. So, I already know that alarm has gone off or it has not gone off. By additionally knowing whether earthquake occurred or it did not occur, does that change my probability distribution about whether John is going to call? John only depends on alarm. If alarm is already known to me, I have idea of how John is going to behave. Any additional knowledge about earthquake and burglary does not actually give me information. So, we can say some conditional independences here. We can say that John given Mary, alarm, earthquake, burglary only depends on alarm. If I know alarm, all the other things do not give me any additional information. Similarly, for Mary, we can also say that earthquake given burglary is earthquake because they are independent. Now, we are given all these conditional independences. Now, it is very easy to use the chain rule. So, what is the chain rule? John, Mary, earthquake, burglary and alarm. This is a joint distribution. You can always write it down without anything as P of B times P of E given B, P of A given EB, P of M given AEB, P of J given MAEB. But P of A given B is P of E, M given AEB is M given A, and J given MAEB is J given A. So, therefore, alternatively this would become, because of the conditional independences, this becomes probability of earthquake, probability of burglary, probability of alarm given earthquake comma burglary, probability of John given alarm, and probability of Mary given alarm, and the product of these 5. And if you think about the graph, what have we done? We have simply multiplied all the CPTs. CPTs are conditional probability tables. So, for a given joint, so suppose I want to know what is the probability of John, not Mary, no alarm, earthquake, no burglary. So, I will say earthquake 002, no burglary 0.999, alarm, no alarm. No alarm given earthquake, no burglary would be 0.71. John given no alarm would be 0.05. Not Mary given no alarm would be 0.99. I will multiply all these 5 numbers, and that gives me the joint probability for this particular state. So, what I have done is I have shown you with an example, and this is true in general, that a semantics of a Bayesian network is that the full joint distribution is nothing more than a product of all the conditional probability tables. Product for all I, where I is a node, probability of xi given all the parents of xi. And because it is an acyclic directed graph, because it is acyclic, you can start in the topological order. You can start from the parents of everything. There will always be some node which has no parent. Now, you have defined it. Now, there will only at most be one node which has a parent, which would be something you have already defined, and you can keep using those probability values in the right CPTs to do all the multiplications. So, this is nothing but a factorization of the joint distribution. In 10 parameters, I have been able to represent the full joint distribution, which would have otherwise taken 31 parameters, because there are 5 variables, each variable can be true or false, there are 32 states, they all sum to 1. So, there are 31 parameters. Something that required 31 parameters has now been done in 10 parameters, because there were conditional independences in the domain that we were able to exploit. Any questions at this point? Yes. How will we determine the probability? So, that is called learning, and we will talk about that in 4th class from now. Okay? So, first we are defining what Bayesian network is, then we will ask queries from a Bayesian network and make inferences. So, given the Bayesian network, we will try to figure out what is the probability that if alarm went off and burglary happened, what is the probability that John called but Mary did not call. These kinds of questions we will answer, and once we when John has called, what is the probability that burglary has not happened, and questions like that. Then we will talk about how do we learn Bayesian network. So, we will talk about it in the next 3-4 lectures. This will get clearer and clearer to you. Okay. Yes, Sukriti. Is it possible that a Bayesian network can have an edge from earthquake to John calls? Is it possible? I believe it is possible, and it is possible if we choose a bad order of making the Bayesian network. Here is a simple example. Suppose alarm is the parent. Suppose we start with making an edge from alarm. Then does alarm influence earthquake? Now, it is very weird to think in the non-causal direction. So, therefore, it becomes confusing, but does alarm influence earthquake? Yes, because if alarm goes off, then it increases the probability of earthquake. If alarm does not go off, it decreases the probability of earthquake. However, if I know earthquake and alarm and I want to figure out about burglary, is any conditional independence happening here? It is a hard question. The reason it is a hard question is alarm going up increases the probability of burglary. Alarm going up and earthquake also happening decreases the probability of burglary. So, in fact, in this weird order, both earthquake and alarm actually influence burglary. So, if you take a very different order, of variables, then you can get a very different Bayesian network structure and then influences. So, therefore, the general principle here is that it is intuitive to think about these edges in the causal order, but probabilistically, theoretically, mathematically it is not needed. They can work even if these edges are not in the causal order, except that thinking about it humanly is less intuitive, that is about it. Okay. So, now what we are going to do is we are going to use the Bayesian network to think about what are the conditional independence assumptions it is making. And after that we will start talking about how do we do inferences. So, inferences like, suppose I want to make this inference, let us say I want to know that John has called, Mary has called. What is the probability that burglary actually happened? That is a question, that is an inference question, right. We want to compute some probability of some variable given some other variable. I mean, these kinds of Bayesian networks are incredibly common. For example, this is a car diagnosis Bayesian network. It basically says that battery age I can observe, battery meter I can observe, whether battery is dead or not I cannot observe. I can observe that there is oil and light is on or not, but I also observe car is not starting. So, what is the likely causes? Now, this is exactly the diagnosis kind of question we did in logic also, except we now will have probability distribution of what is the more likely cause of a certain event and what is the less likely cause of a certain event, right. Similarly, car insurance, believe it or not, a lot of car insurance and figuring out how much should we give you insurance or not, how much your premium should be, depends on a lot of factors, and all these factors in a complicated way are dependent on each other. So, what is your age? If you are a very old person, then you might get a senior citizen discount, but if you are too old, then you may not be able to have good reflexes, so your premium should go up. If you have a good socio-economic status, that would be one thing. What kind of mileage you have on the car? If your car is too old, then they want to increase your cost, but they also want to decrease your premium because now your car is cheaper, so it will cost them less money, etc., etc. So, there are all these factors which are all dependent on each other. Your driving skill depends on your age, your driving quality depends on your driving skill, whether you are going to have an accident or not depend upon how good a driver you are, whether you have airbags or not, do you have anti-lock system or not. Again, some of these things you can observe. For example, you can observe the vehicle year, you can observe the age, you might not be able to observe the driving quality, right. You should know whether there is an anti-theft device or not. Anyway, the point is that all these factors probabilistically come together into determining how much should be the liability. And this Bayesian networks has had a huge number of applications. In medical diagnosis, what is the probability of the disease given the symptoms, in computational biology, in natural language processing, what is the parse tree of whether a word is a verb or a noun given the sentence, document classification given the document, is it of class sentiment, positive sentiment or negative sentiment, in image processing given the image, is it of is there a boy in there or not, robotics given these sensor readings, how far is the actual obstacle. There are so many cases where you have to ask these questions and their answer has to be probabilistic because the world is probabilistic, either because we can't observe or because our sensor makes mistakes or because whatever. And for all such situations, some kind of probabilistic graphical model becomes the basis, and Bayesian networks is the first fundamental probabilistic model which we are doing in this class. So, what we are doing is actually incredibly important, even though deep neural networks have become much more important in terms of real practical applications. Bayesian networks and their power is believed to be coming back in a little while. Also, for some better accuracy, sometimes we combine the two, like the best model for sequence labeling is a bi-LSTM CRF. A bi-LSTM is a neural network, a CRF is a probabilistic graphical model. So, the deep network does something and then the probabilistic graphical model does something, and together they make the best decisions. So, therefore, I think that Bayesian networks is something that is incredibly important for all of us to study, and in the next class we will talk about deseparation, the general principles of conditional independence, and then we will get to how to make probabilistic inferences using a given Bayesian network. You can stop now.